Good afternoon, good morning, depending on your time zone, if you're in the States. It's a great pleasure to kick off this international webinar with our Malawi partners about seismic safety and resilience of schools in Malawi. This is a joint project that we implement along with people that will present you in a while. You can see their names on the first slide, but before we progress with our presentations, I would like to share with you some kind of guidelines in order to help us make this webinar as fruitful and efficient as possible. So for the speakers, a kind request to keep up with the time and to mute yourselves or hide your video unless you're talking. And for the attendees, if you have questions, please use the chat button to text your question while the speaker is presenting. We will also have some time at the end of the session for live Q&A questions and answers, but you would need to raise your virtual hand. There is a button at the bottom of your Zoom screen called Reactions. If you click it, you'll see that there is a link to raise your hand, and then you'll be given the chance to talk. We're very interested to hear your ideas, how we can improve about everything we're currently doing. So this discussion should be, it's expected to be very, very interesting for all of us. A final note is that the session is recorded. I hope we have your consent in recording your presence and slides as we will be sharing. So what is this project about? As principal investigator of this project, I'm very pleased to give you an overview about the Safer Prepared, which is actually a merging of two previous projects, Safer in Nepal, Safer Schools in Nepal, and Prepare Africa for Malawi. The objective of this project is to reliably assess seismic hazard for Malawi, structural vulnerability of school building communities in Malawi. This means that we have several different steps, several different work packages. We start with, which actually align with the presentations that you will attend today. We start with a mapping of the active faults in Malawi, and this informs a more accurate representation of seismic hazard. And in parallel, we are assessing numerically and analytically the vulnerability, how weak the school buildings are, with the aim to quantify, prioritize their strengthening procedures based on the relative risk that it's quantified and monitored with the use of some tools that we will present, a mobile app and a web app that we'll be discussing in short. And this practically means that at the end of the day, we aim to digest all the information and the research we are doing along with our Malawi partners and create some tools that are rigorous inside and quite complicated, but they're very, very simple to use with a very easy interface, deploy them fast to collect the first data and contextualize for the country of Malawi, to train the people by webinars and also by physical presence and co-design the strategy for national implementation. Doing community engagement, unfortunately due to COVID, we weren't able to do that extensively yet in Malawi, but we hope that during the summer things will improve and we will share with you more information, and then actually deliver, transfer the ownership for everything we do for the people and the country of Malawi, so that you can use them with us and without us in the future. You will hear more about that in the next presentations. In the meantime, feel free to use to visit our Safer Prepared website, where we will be also uploading the outcomes of this interesting webinar. So without further ado, I would like to invite Ignasio Ngoma, Innocent Kafodia, and Hassan Dalla to present the importance of Safer Prepare for Malawi. I would like to stress that the contribution of all three of them has been great, precious, I would say, for our project. We wouldn't have made any progress without their aid, and we're very grateful for helping us organizing this webinar. So Ignasio,
thank you
the floor
very
is
much.
yours.
As has been said, indeed, on the Malawi side, we have been working closely with Hassan, Innocent, and myself. And in this presentation, I'm just welcoming you all to ensure that, we have had some interactions with the local participants. Next, Joe. Okay. I'll just talk about the introduction on the building data collection exercise and the community resilience sessions. Next. So in terms of the introduction, my role is simply to welcome you all in this particular workshop. There are Malawi participants, UK participants, particularly the University of Bristol and other participating universities in the UK, as well as the World Bank participants to this virtual workshop on Safer Prepared project in Malawi. The Malawi participants, most of them recall that we had a Safer Prepared project, which I think we are building on the achievements that were made, so that in this one, if we look at what was achieved through the Safer Prepared project, we can be able to play a very meaningful role. In the Prepare project, Africa project, we established that Malawi is actually a seismic zone. The whole of Malawi is a seismic zone. We also established particularly houses, the type of houses we have, and their capability to resist resilient levels when a seismic activity has taken place. And in that one, some interventions were developed, which we can be able to utilize when an earthquake comes up. Now for Malawi, a number of stakeholders have taken part in the Prepare project as well as this one. In this one, we have University of Malawi, Polytechnic and Chancellor College as the players in the project of geological survey. We have Ministry of Education, the IMU and the basic education primarily. Then we have Ministry of Transport and the Public Works. We have Ministry of Housing and Urban Development, University of Malawi University of Science and Technology, and the DODMA. These are already playing a part. Next, please. This Safer Prepare project aims to develop an app that can be used to report seismic impact in schools. As we know that when these seismic activities happen, normally schools, for the experience in Malawi, have been used as areas people can go and assemble, but also the students, also the people that is, and teachers do have quite some challenges. And so in this particular project, as we will see, we'll find ways of ensuring that when these things happen, we have at least a better way of reporting it. Now, there will be two aspects. You can go to the previous slide. In terms of, next one. In terms of our role as Malawi stakeholders, we have two parts to play. One is in data collection. As just mentioned, we have schools that are built. So we're looking at the actual learning blocks, as well as the teachers' houses, how they are built, so that we have clear typology, and therefore be able to put them into the app that is being developed. So the project involves schools in Malawi, and so district education managers will play a major role in identifying sample schools, as well as facilitating actual data collection. The IMU, Ministry of Transport and Public Malawi Housing Corporation, Ministry of Housing and Urban Development, as well as establish the typologies, but also how much it takes to build the houses, in this case, teachers' houses, and of course the learning blocks, so that at the end of the day, if anything has happened, has been properly coded, we can be able to quickly assess how much it may. Next. In terms of community resilience, which has been mentioned, there will be need to interact with the the people involved in the management of schools. And as you can see there, that the educational managers will continue to play a very big role in facilitating, organizing the various players in school management. We are looking at the head teachers, teachers themselves, and school management committees, the school children, parents, school workers. In terms of school workers, we're looking at those who are generally available at the school. We do have guards, cleaners. Those are also important in terms of looking at their role in this one, as well as community leaders. In terms of community leaders, we're looking at the chiefs and others, including elected officials. Next. So in terms of our role, particularly as the Malawians, in whatever role we are playing a part, will be significantly contributing in terms of the data that is to be obtained, and also to look at how communities can react. So there is here questions that you will see from the presentations. We're looking at indeed various aspects, how communities cope when an earthquake has happened, and so forth. So I thought that I should talk about this one so that you are prepared to look at the coming in presentations. Thank you very much for your attention.
Thank you very much, Ignasio, for your valuable introduction. I would like now to yield the floor to Professor Juliet Biggs to talk to us about seismic hazard assessment and awareness.
Yeah, thank you very much, Tassos. It's great to see so many familiar faces here today, and also some new faces. So I think many of you know me already. I'm from the School of Earth Sciences, and I'm going to talk a little bit about earthquakes in Malawi and in East Africa in general. So many people are slightly surprised that we're working on earthquakes in Africa, because the perception is that the risk associated with earthquakes is low in Africa. And that's not entirely true. So seismic risk is actually made of three components. It's composed of the hazard, the exposure, and the vulnerability. So in Africa, the hazard comes from the East African Rift, which is on a plate boundary that extends from Ethiopia in the north through to Mozambique in the south and runs through Malawi. And the spreading rate is quite slow, so the earthquakes are infrequent, but you can clearly see a band of earthquakes running through the continent. The exposure in Africa is very high. There's a high population density. And as you can see from this map in the center here, a lot of that's actually associated with the Rift Valley. And perhaps most importantly, vulnerability is extremely high. And that's largely because the quality of the buildings means they're very vulnerable to seismic events. So when combined, these factors lead to a high seismic risk. And addressing this actually aligns with many of the UN Sustainable Development Goals. The first three I've listed here, numbers 1, 11, and 13, are all related to environmental shocks and improving the resilience of, firstly, poor people, sustainable cities, and finally linking that with climate action. And the final one here is associated with international cooperation and sharing technology between nations. So addressing the challenge of seismic risk is very important to the UN and to the Sustainable Development Goals. So I've mentioned that there are earthquakes all through the East African Rift, but if we zoom in on Malawi, you'll see that the red lines, which represent the faults, run all the way through the middle of Lake Malawi, and then through the densely populated area of southern Malawi, past the cities of Zomba and Blantyre. And this is an active continental rift zone. And in recent years, there have been two notable earthquakes. Firstly, the 1989 Salima Dedza earthquake, which was a magnitude 6.6 earthquake and was actually quite deep. And more recently, the 2009 Karonga earthquake, which was a magnitude 6 earthquake that happened in the north of the country. So this earthquake was actually a fairly small magnitude. There was a sequence of earthquakes, the largest of which was this magnitude 6, and it occurred in a very rural area of northern Malawi. But even so, it actually caused a lot of damage. It caused the collapse of over 1,500 buildings and major damage to several thousand more. But actually, this is one of the smaller earthquakes that might happen in Malawi. What we know is that these earthquakes occur fairly infrequently, but the instrumental record in Malawi is much shorter than many other countries around the world. So many countries have records extending back many thousands of years. In Malawi, the record of earthquakes really only extends back as far as 1950. So our knowledge of what happened in the past is very limited. So in order to overcome that, we have to look at the landscape and see where the earthquakes are recorded. So earthquakes occur on faults. And when an earthquake happens, the ground moves and it leaves what we call a scarp in the surface. So we've been working very closely with the Geological Survey, and in particular with Hassan Madala, and there's a picture of him here, on the fault scarp that runs close to the city of Zomba. It's called the Zomba Fault. And this scarp is about 30 meters high, and it extends for 50 kilometers. And we can estimate the size of the earthquake that would have caused this fault scarp. So if we look at the global compilation, which is plotted on the right here, we can see that a fault length of about 50 kilometers corresponds to an earthquake on about magnitude 7.1. So in order to form this this fault scarp, we know there must have been an earthquake of about magnitude 7 sometime in the last few thousand years, but we can't give a precise date. So what we've been doing with the Geological Survey Department is mapping out all of the faults in Malawi, and we've started off focusing on this region of southern Malawi here. And what we found is the faults extend all throughout the country, and they have the potential for earthquakes ranging between magnitude 6.5 and right the way up to magnitude 8. So that's significantly larger than any of the earthquakes that have been recorded in the last century. However, these earthquakes are likely to be quite rare. So on each fault, the return interval is 1,000 to 10,000 years. And we've actually systematically compiled this information. And if you follow that link, you can get to a database you can download and look at yourself. It's in a GIS format. And if you need a copy of that link, we'd be very happy to send that to you. So this information allows us to imagine what might happen in individual earthquakes. So here's an example. This is an earthquake on the Bilila segment of a fault called the Bilila Matakataka fault. The earthquake would be about a magnitude 6.7, so not a particularly large earthquake by Malawi standards. But even so, it's in a much more densely populated region than the Karonga earthquake. And we estimate an earthquake here would affect about 500,000 people and cause the collapse of about 70,000 buildings. And remember, this is still a fairly moderate size earthquake for Malawi. But this is just one scenario. As I said, there are faults running all through the country. So we need to think about what's going to happen overall. And to do that, we come up with something called a probabilistic hazard map. And this looks at the overall shaking level that you might expect in any part of the country. And I've shown two examples of these maps here. The one on the left comes from an international project called the Global Earthquake Model. And that shows you the sort of shaking that you might expect if you just looked at the instrumental record of earthquakes. So there's earthquakes that have actually been recorded in the short record in Malawi. And the picture on the right is what we get when we include the information from those fault scarps. As you can see, the estimates of shaking are significantly higher. So these sorts of maps can be used for risk assessment and also for developing building codes. And we're currently working on these so that we can include them in the new Safer Prepared app that's being developed, which focuses specifically on school building safety. And you're going to hear more about that from the next presenter. Do we have time for a quick question, Tassos?
Yes, we do. The floor is open for a couple of questions. Please raise your virtual hand if you would like to participate and ask a question live. While waiting for a question to come from the audience, Juliet, is it common that in some regions of scarce recorded motions, the difference is quite high as you present in Malawi when you include that faulting?
Yeah, so these faults are unusually long and unusually high. So the unusual length tells us that we have the potential for very large earthquakes, much larger than many other regions of the world. And the height of the scarp is perhaps a clue, and this is something we're still working on, but we think that many of these scarps were actually formed by multiple earthquakes. And actually the offset in each earthquake is probably more like 10 meters. And when we see 20 or 30 meter high scarps, that's recording 2 or 3 earthquakes that have happened in the last few thousand years.
Mm-hmm. So you also talked about evidence of 50 kilometers footprint of the fault at the surface. That is evidence of a very high 7.1 magnitude earthquake that happened in the past. Is there any historical documentation that can help you somehow assess when this happened? Or
Yeah, it's very limited in Malawi. We don't have any evidence of such large earthquakes in Malawi, but there is evidence elsewhere in the East African Rift. So there was an earthquake in the early 1900s in Tanzania, just to the north of Malawi, that would certainly have affected the northern portion of Malawi, that was in the magnitude 7s. And there have been a few others elsewhere in the East African Rift with faults that look extremely similar to the ones that we see in Malawi. So we think this is probably a good estimate. So although they haven't happened in the last 60 or 70 years in Malawi, they definitely do happen.
There's a question by Sean Wilkinson. Sean, please unmute yourself.
Hi, thanks very much, Julia. That was great. Sorry, I'm a structural engineer, not a seismologist, so apologies if this is not that great a question. But what about the? Have you got any handle on the sorts of depths that these earthquakes are likely to be? Because that obviously has shallow ones obviously have or the depth of it has a big impact, and I'm not. Anyway, that's the question.
Yes, no, it's a great question actually. So what we do know about Malawi is that the seismogenic thickness, that's the depth to which earthquakes can occur, is unusually large here. So you can get earthquakes as far down as 30 or 40 kilometers. And from a geological perspective, that's very unusual. So that means some of the smaller earthquakes might be quite deep. And we're currently trying to work out how to include that in the probabilistic hazard assessment maps that we produce. But actually, all of these earthquakes that are recorded as fault scarps, by definition, have to have broken the surface. Yeah. So anything that we can see as a fault scarp means that there were at least one earthquake there that broke the surface. So we know that many of them are shallow, but there's probably the difference between the Salima earthquake and the Karonga earthquake. The Karonga earthquake was extremely shallow and caused a lot more damage.
So does that also then mean, so since there's not a lot of instrumented records and you're looking at historical stuff, you can only get the stuff that's basically expressed at the surface, and therefore you might be missing some very big I mean, they might be in the historical record, either oral or written, but yeah, is there potential of missing those?
Absolutely. So the very largest earthquakes probably do have to rupture the whole seismogenic thickness, so they would break that whole layer and they would break the surface. But we could certainly be missing some other ones. But we can, other moderate size earthquakes, I should say. But we can also play some games with the fact that we know the whole of that zone has to be straining kind of uniformly. It's very difficult to get the top bit stretching and the bottom bit not stretching. So if we can have an idea of what's happening in the top layer, we can make some guesses about what might be happening lower down. And as you say, those lower earthquakes are probably less important from a structural point of view. So it's important to include them in the catalogue, but the precise details, if they're not in quite the right place, it's probably not so important.
Brilliant, thank you.
Thanks very much, Sean, and also Juliet for this excellent presentation to create awareness that just because we don't see the earthquakes, this doesn't mean that they can't happen. They can happen also in Malawi, and it's extremely important faults to be mapped to influence and inform the PHA, the probabilistic seismic hazard assessment maps that we're using for risk assessment and loss quantification. It is equally important to discuss about how we can assess probabilistically the performance of structures and school buildings during an earthquake. And I would like to pass the floor to Professor McDonald and Dr. De Risi to talk to us about this very important topic.
Yes, perfect. So, hello everyone. Today I am Dr. Raffaele De Risi, lecturer in civil engineering at University of Bristol. I am going to present today the work that we have done together with Professor John McDonald and Dr. Nicola Giordano, which is the main postdoctoral research associate on the project. Basically, we needed to create models that can be fed in the app. And as Juliet was mentioning, the risk is the product of exposure, vulnerability, and hazard. We focused on vulnerability. So what is the best model that we can develop for the vulnerability assessment? Is certainly a simple function that represent somehow a group of buildings, a group of structural elements. Now, the journey to do so, it's quite long, it's not easy. Because first you have to be able to identify the structural topologies, and therefore you have to make yourself an idea on what is the portfolio of structures. Then you have to identify the material properties, and eventually do some analysis. And only at the end you can basically fit some functional models that can be then eventually fed in the app. So the journey started with very global large-scale analysis, where we started from the census 2018, just to understand the level of scolarization. Then we have the precise map and location of primary schools and secondary schools. After that, we started to do a small exercise, and therefore zooming in Google Earth, because we were not able to go and have a proper survey. We started to discuss a little bit about what is the geometrical configuration of classrooms, administrative buildings, and so on. And eventually, you can come up with a sort of geometrical portfolio identification of the structure that belongs to a specific typology. We also, in lack of a proper survey, we also relied on some of the pictures we obtained during the previous field mission. This is one of the pictures that Dr. Luke Wedmore actually shot in one of his field mission. This is for the MUA school. But also we kept an eye on the new structural typologies that the government is building, and also that NGOs are building across the country. And we came up with a structural identification that somehow is consistent with what we already knew about residential. And in fact, is consistent with the Klukinas et al. Paper available on Journal of Housing and the Built Environment. The classification of buildings is realized according to PAGER, which is a prompt assessment of the global earthquake for response. And then we have also the European classification, which is the European macroseismic scale. As expected, one of the main categories certainly are reinforced fire bricks masonry. Then we have confined masonry of buildings, and the new category of buildings that are realized are certainly stabilized blocks. Now, the geometry is not enough, the structural typology is not enough. We needed also some information about the material properties, and we did a very extensive experimental campaign in Malawi at the MAST Polytechnic laboratory. And we got some experimental results that we were able to match with the numerical models, and therefore to come up with some sort of quantification of the material properties. So now we have a proper identification of the structures, of the geometries of the portfolio. We need to do some structural analysis. And for structural analysis, we relied on the worst hypothesis ever, which is the lack of connection between orthogonal walls. This allows you to do the assumption that you independently in plane and out of plane facades, as we did. So this is the classical in plane behavior, and this is the classical out of plane behavior. Now, all of us is aware that earthquake is cyclic, and therefore when you basically apply an earthquake to a structure, it damages in a very asymmetric manner in some areas where you have a concentration of damage. For our analysis, we relied on a simple analysis, the pushover analysis, that basically is just pushing the structure in one direction. From these curves, it is possible somehow to derive the final outcome, which is a fragility curve. What is a fragility curve? A fragility curve is a surrogate model, is a functional form that condenses with a few parameters the behavior of a specific structural topology and of an ensemble of structural geometries. So you can obtain these fragilities for different damage state, from no collapse up to complete collapse, in this plot from green to yellow. And they represent, for a given intensity measure, the conditional probability of observing a given value, a given level of damage. So the red curve is complete damage, the green curve is no damage at all. So we did this operation for each building. We separated the two walls, studied in plane and out of plane, and then with the conventional and consolidated methods such as the SPO2-IDA and the capacity spectrum method that are very consolidated tools, we transformed all the pushover curves in fragility curves. The gray line that you see here are representative of a portfolio of structures, and the easiest thing to do to come up with a single fragility is certainly do the average and take also the variability of it. And this is the function that is eventually implemented in the app. These are our results for the case of reinforced masonry buildings. And you can appreciate here that the scale is different, and therefore the out-of-plane is certainly a dominant phenomenon with respect to in-plane damage. And when you solve the out-of-plane damage, you can actually study only the in-plane damage that is also consistent with some fragility curves that we borrowed from GEM, the same global earthquake model that Juliet mentioned earlier. This also underlined the necessity and importance of cross-connection between orthogonal walls. So in conclusion, now we think we have a good understanding of structural topologies and materials. And we combined the methodologies developed in safer schools in Nepal and PREPARE project in Malawi, and to obtain new results that now can be implemented into the. So thank you very much for your attention.
Thank you very much, Raffaele, for this very interesting presentation and also for keeping up with the time. So we can move to the next presentation, which is about the concept and application of pre-earthquake inspection of schools. So we're going to show you a brief overview about how the mobile app and the web app is working. But above all, I would like to present you the concept, actually, of pre-earthquake seismic risk assessment and strengthening of school buildings. So just to check with you that you can see my slides. Is this confirmed?
Yeah.
Okay, thanks very much. So I would like to stress here that pre-earthquake inspection of buildings takes place all over the world. In developed countries, believe it or not, there is about 50 to 60% of buildings whose seismic performance is inferior compared to buildings that have been designed to modern codes. And also, there is no country in the world that can actually strengthen all the buildings that require strengthening before a future earthquake. This means that in all countries, from the most developed ones, the States, let's say, or Japan, or other countries in Europe, to the developing ones, there is a great need to allocate resources and funds in the most smart way that can create the maximum impact, which means it will address the maximum risk where it exists. Juliet presented already the concept that dealing with risk is not about dealing with the weakest structures that Raffaele presented. It's about dealing with the convolution, which are the weakest buildings that are exposed to the highest level of seismic hazard. At the same time, they involve the highest number of people, of students, of assets in at stake. So this is the concept why all over the world, rapid visual inspection of buildings has to be made very, very carefully and efficiently. Secondly, it is important to state that because the earthquake has stochastic properties, Juliet presented cases that earthquakes happened in an unknown time in the past, but they have been very strong. So there is a probability of things to happen. This means that our calculations to prioritize the buildings have also to be based on some probability. And this probability relates to the fragility estimates that Raffaele presented. So for a given intensity measure like PGA or spectral acceleration, let's say, depending how strong the earthquake can be, there is a specific probability of different structural types to collapse or not. And this is what exists in the heart of the pre-earthquake inspection strategies all over the world. Now, the problem is that most of these techniques and procedures that involve structural vulnerability, seismic hazard, soil conditions, and all these factors are tailored to each different country that they are aiming to be implemented in. This means that in Malawi, we cannot actually take methodologies that are developed in the States and apply them. Not even the ones that we developed for Nepal, which were also tailored. We need to develop procedures that are very relevant and contextualized to Malawi per se. This means that we need to identify what are the structural typologies that are most common for school buildings in Malawi. We need to identify scores and probabilities for them, see common deficiencies that exist for the structural portfolio and the building stock in the region, probably also in different cities between urban and rural regions. We need to adapt the methodologies and then repeat all the calculations that we are doing in other countries, specifically for Malawi. So this is the quest we are currently working on. And in fact, in a more general sense, if you collect or zoom out a little bit among different countries, you will see that we've got a database of 42 to 45 different typologies, structural types of buildings, different features and different materials, different structural configurations, and different performance at the end of the day. But for Malawi in particular, and for school buildings, we have identified the 5, let's say, most commonly used typologies. This doesn't mean that in the database and in the software, we don't cover for the rest. The software is wider and covers all possible structural topologies we can find. So we can also cover a steel building or a precast or, a building according to the seismic, the latest seismic codes, if it exists. But the most widely used buildings were the ones that we focused in order to produce more realistic estimates of structural fragility. And you can see which are these ones: unreinforced fire brick masonry, reinforced or confined masonry, that is also very common all over the world, unreinforced soil stabilized blocks, SBBs, adobe structures, earth blocks that are unreinforced, and some engineered, which means kind of code compliant reinforced concrete structures with typical masonry infill walls. In most of the cases, we're just talking about one-story buildings, as you know better than ourselves in Malawi, but also the database covers the case and the distinct relative risk for buildings that are 2 stories or even higher if they exist in the capital. And then having done so, Raffaele presented how, following standard methodologies, we have been deriving fragility curves based on the analytical capacity curves. Capacity curves are these expressions that relate the lateral force, let's say the seismic force, with the displacement, because the displacement is a proxy of damage. The higher the displacement, the higher the expected damage. So all this actually is a series of thousands of scenarios that we're running for different buildings with different intensities of earthquakes, with different probabilities and uncertainties on the material side, on the capacity side, on the demand side, which is the intensity of the earthquake in a specific region. So the same building can be equally weak, but when located in a region with higher seismic hazard, then the total risk will be higher. And if that's the case, the methodology we're developing will prioritize this building. This would make good use of our limited funds to strengthen this particular building. So this is the concept in short. And of course, there is some scoring that seems to be simple in the table, in the database, and in the software, but behind each number that you see here is a probability of collapse. There is a model, there is hazard, there is active fault mapping, improvement of PSHA models, and so on. So our effort is to make complicated things look very simple and be able to be implemented in a local context. So apart from the structural typologies and the local hazard in the area we're talking about, it is also very important to adapt the scoring. So we give a score, as I said, to every single building, depending on some deficiencies or vulnerability features that we observe. So in this case, that's clearly an inadequate connection of walls, probably lack of corner elements that connect to perpendicular walls, lack of diaphragm action, which means that it is very easy for the walls to fall out of plane. That is very dangerous. And then the roof, even though it's light in most schools in Malawi, it's going to just fall down and jeopardize the stability of the building, and also might lead to fatalities in the school buildings. And also we can observe cases where structures don't have a very, let's say, normal, regular shape. This is always an aspect that has to be accounted in seismic codes. When structures have been designed with such features, there is no problem. When this was not taken into consideration, we take it as a source of vulnerability in the system. For reinforced concrete buildings, that again, we know that for schools are not very relevant in Malawi, so I'm going to skip them. But just to give you an idea, wherever there are weak points like this, called short columns, columns that don't extend to the full height, where during an earthquake, they will fail in shear abruptly and in a fragile manner, even though they bear vertical loading perfectly well. So this is always a very bad surprise. After an earthquake that can happen all over the world, we subtract points for that as well. When there is corrosion, or when there is low quality materials, low quality concrete in this case, or cracks in the walls that we can observe, for instance, in masonry buildings, or even in infills of reinforced concrete buildings, then if we see that, we subtract points. So the purpose of the app is to ask engineers to see things on site, click the button, I've seen this, and then the software will subtract points that are calibrated to meet the mathematically rigorous probability of failure that is caused by this particular feature. In this case, that's a non-structural feature, is when we're building on slopes. This is always more dangerous because the foundations can be uneven, or because we can have site amplification. Earthquake ground motion becomes stronger in strange topographies because waves are reflected within the soil medium. And clearly, when we see disorganized masonry or low quality mortar, either mud mortar or even lime mortar, when we see visually things that are not convincing, that can bear the lateral load of an earthquake, then we just report it in the app, and the app will do the business and will provide the appropriate score. So assume that we do that in theory for all school buildings in Malawi, then this will give us a relative score. The absolute score doesn't mean that much, because what if score is 3 or 3.1 or 4 or 4.1? But the relative score, which are the 10% of buildings that are both exposed to high seismic hazard and are weak enough to trigger attention, this will be highlighted as priority A, which actually doesn't mean that they have to be strengthened immediately. They just say, well, out of 100 buildings, these are the 10 that we will need to see again. Why? Because before we make a decision, we always want to do some rigorous engineering calculation and apply some strengthening techniques after having done some thorough investigation. But it's a very good screening. We filter out the 10% of, let's say, most exposed to seismic risk school buildings. And this is actually exactly the same procedure that is followed worldwide. It is just that all the numbers, all the typologies, all the materials are contextualized for Malawi, and the hazard, as Juliet presented previously, is also contextualized for Malawi. And then this actually would lead to how does this look like in this app and web app. So you can see here how we implemented that in but now this app involves both different aspects. So it's actually two software into one app that cover both Nepal and Malawi. You have to pick the flag for Malawi to follow the particular typologies and scoring that relates to Malawi. But you can download it for free in Google Play. Actually, you can do it as I speak. It's actually in beta form, because we would like to first have a field campaign with our colleagues in Malawi and make sure that we will be able to test it, improve it, update the scoring, update perhaps typologies, add some local vulnerability problems that maybe we haven't thought about, and they're very, very localized in some regions. So the more we apply it, the better it becomes. But clearly you can download it as we speak and start working with it. The only thing you won't be able to do, because it's actually free A to Z, you can play with it and rank or score your school or the house you live in. However, unless you ask us for a code, you won't be able to sync to the server. But for an exercise, you can certainly use it. So how does it work? Actually, all the mobile phones act like a client. You don't need to have web access. You don't even need to have 3G or whatever 2G you can have in the field, because you just use your normal phone, take photos, and report what you see. Location is tracked automatically. And then once you get to a Wi-Fi in your office or your own home or wherever you can find internet, you can just sync with a database. So no need for internet access. It works perfectly well offline. And this is pretty much how it looks like. You pick the country, you pick new school inspection, you do pre-earthquake assessment and not post-earthquake in this case. And then there are some questions that are general and some others that are tailored for Malawi, like picking the province and picking the district to say exactly where you are, even though if your phone provides the GPS location, this will be done automatically. And then in terms of general data, you can decide or inform the system, the app, whether it's a primary school, a secondary school, a higher school, and so forth. Now, you can choose from different structural typologies. Like I said, there are 5 most popular for schools in Malawi, but the database gives you the opportunity to pick more than these 5. It gives you actually access to all the typologies that we have reported for the different countries we are working in. And the most interesting thing is that for every different typology, it gives you some photos. So if you're not really certain, you can just see the photos and see whether it looks like how you're planning to classify it. And then when we log in the web system, we can also amend it and update it as we see fit. Another very interesting thing is that all the maps that Juliet and Max have, and Jack and Luke have prepared for Malawi, all the seismic hazard maps, are automatically imported and provide a scoring without doing anything, because the phone normally knows where you are. And this means that there is a point that is overlaid in the seismic hazard map, and the software knows exactly where you are and how exposed you are to the seismic hazard. So this is done automatically, and you don't have to decide it yourself. You don't have to rely on any other person to make a decision, not even say where you are. This is fully automated. But what you do have to report is some vulnerability aspects that I presented previously. Do you see this? Do you see that? Is this weak? Do you like that? Do you think this is stable? Because all these yes or no's, well, the no's subtract some points from the analysis that you're doing. And once you do that and you're able to sync, all this information goes into the web app. Why do we need that to go to the web app, apparently behind a firewall, and to go into the server? Because we would like the authorities to be able, this is the example how it looks like with 1,200 school buildings already monitored, recorded in Nepal. This gives you the exact location and the exact score of every single school that has been assessed in the country. And this is a very useful tool because it doesn't require to install any software. You just use the username and the password that we decide together, and then the authorities, the Ministry of Education or the provincial inspector or whoever who is responsible for the school portfolio and the safety of buildings is able to see in a relative sense which are the reds, priority 1, which are, let's say, second priority, which seem to be very safe as we speak. So this is precious information that you can get in 0 time, actually. Imagine that about 10 years or 15 years ago, when an earthquake was happening worldwide in the most developed countries, it was taking 6 months for this map to be filmed. Same for inspections before an earthquake. It was all taking too long. Now it's fully automated and you just need to download the app and connect to the web app to have access in this information. And this information gives you also some statistics that are extremely useful, like the relative score of different structural types. Because if you identify exactly which are the weakest types, then you can also combine them with a hazard, which is actually already included in the score, and decide where you intervene first. Or it can also show you, like I described previously, rank all scores of all buildings within the same scale. Clearly, the ones with the lowest scores, relatively speaking, it doesn't matter what this number is, relatively speaking, these are the school buildings with the highest risk. So if we have funds to strengthen 3 buildings, 10 buildings, 20 buildings, well, we'd better invest them wisely to have the maximum impact and mitigate where it is mostly needed. And then you can have access to all the photos. We can actually amend the information that it is reported. So if you don't feel very confident, there's a question at the end. Are you confident about the data that you have filled in? If you're not, we can log into the system together, discuss the data, improve them, correct them, and make sure that whatever we provide is accurate. As a final set of slides in this last minute, Professor Agarwal is going to talk to you about the similar type of assessment, but this time not focusing on school buildings, focusing on the resilience of the community. Because we might have very strong buildings, but if the community requires some strengthening in terms of planning to support the life around the buildings, then just strengthening the buildings is not enough. It's clearly more and mostly about the people. So he will be talking to you about how you can also assess the community in a self-assessment scheme. And these are just some snapshots of how the app looks like. So I think I have exhausted my time. Probably there is 1 minute for a question, but I would prefer actually to give this minute to the next speaker because I don't want to abuse my role. I can simply answer at the end of the session if there is some time. So with your permission, I would like to yield the floor to Jitendra Agarwal to talk to you about community resilience metrics. Thank you for your attention.
So I'm going to talk about the resilience of educational communities a bit in detail. This is the Bristol team, and we're working with the Malawi team in understanding the communities. So why do we want to talk about resilience? So as you heard about the safety of buildings, traditionally we design buildings to be safe. However, the natural hazards are increasing in frequency and severity, and we know the resources are limited. We cannot make them foolproof, meaning that we have to try to maintain the functionality of our schools with minimum disruption. And that leads to the notion of resilient schools. So let me try and explain a bit more about the resilience as we are applying in our work. So there are 2 aspects to this. So on the y-axis, we have functionality, and on the x-axis, we have time. So school is functioning well, some natural hazard happens, the functionality goes down, and then the school starts to recover. And under the normal course, it's this path which might take place. When we design school buildings to be safe, maybe there is less impact, and then we can recover. What we want to do is we want to reduce this impact. So we might want to define what is our acceptable threshold, functionality threshold. Similarly, we want to recover faster. And again, different societies might have different recovery threshold. So we want to minimize the impact as well as achieve faster recovery, which means it's not just the school building we are concerned with. We are concerned with all the people who are affected by that school buildings, who contribute to school. And that brings in this children, parents, school teachers, head teachers, and the local community members. So we have to see resilience in the wider context of the educational community, not just the school. And the other aspects which it includes are how a school is governed, how a school is funded, what type of building it is, the social capital, the culture. When I say social capital, capacity of people who in that community to deal with these hazards. So what we did was we started working after the Gorkha earthquake. We developed a set of resilience indicators, which we have been testing in Malawi, and we believe they are equally applicable in Malawi. And the only change we are having to make is supplement this with additional questions given the specific social and cultural background. So we developed a framework. I'll spend a little bit of time on this. So we divided into 4 broad categories. One is the governance and funding, as I said earlier. And this also includes the awareness and preparedness of the school community in dealing with the hazards. So for example, whether there are any drills to deal with any emergency, what is the level of resource? It's not just school building, but the human capital, how well prepared we are. On the other side, structural health, as you have been hearing, that's clearly important, but we also want to make sure that the services to the school, for example, whether school can be accessed when there is excessive rain or flooding, so that is equally important. And then the school community itself, are they healthy? Is there a good working relationship amongst them? How does local culture contribute to building the social cohesion and that ability to deal with any natural hazard by coming together, acting as one community? So we want to consider that as well as the school curriculum, whether it prepares the children to deal with emergencies. So behind these indicators are a set of questions which we use to determine how good the system is. So what we do is we collect data from all the stakeholders, including school management committees, head teachers, parents, children, and the local government and other officials. And as Tasso said earlier, this is collected through a web app, a mobile app, but we also have a paper version where we are not able to use, we can use the paper version. So in the, once we have this data, now this goes to the web where we have this resilience algorithm, which will process all this data and give us scores for different indicators and an overall score. Now, this can be viewed graphically. So what we are seeing on the inside here are the quantitative scores for the different indicators, which are written on the outer circle. But we can map these to qualitative indicators, showing where where the indicators are scored highly or they are good, in green, amber, and red. Once we have identified these, then we can take appropriate action. So we are planning a pilot study as soon as the current situation improves. We'll visit secondary and as well as upper primary schools to collect data, both from urban and rural locations. It's not onerous. Each school data takes about a couple of hours. So just to conclude, a resilient is one which is able to function with minimum disruption due to hazardous events. And we can assess, the resilience can be assessed by stakeholders themselves for long-term planning and taking timely appropriate actions. So that's from me, thank you.
Thank you very much, Jitendra, for this very important presentation on community resilience metrics. Just to clarify that, as you said, community resilience can be assessed by the community itself, whereas to answer a question in the chat box, structural inspection would require an engineer. So these are two different aspects that are complementary, but quite different in terms of who is doing this. Thanks again. Now we can move to the presentation by the World Bank, who has been supporting this and our previous project. We're grateful for this collaboration. I would invite Jingzhe Wu and Angie Garcia Arevalo to talk to us about how we can extrapolate what we're doing for Malawi and contextualize it within a wider level of lessons learned from other countries worldwide.
Okay, so my name is Jitendra Wu, and also we're having my colleague Angie Garcia today, and we're happy to share some experience, lessons learned, and also challenge that we have in implementing our roadmap for risk mitigation solutions and scale for school infrastructure. So first, I'd like to briefly share a little bit the background of the global program for safer schools. So our program's vision is to boost efficient large-scale investments to improve the safety and resilience of school infrastructure and risk from nature hazards and enhance the quality of learning environment for children. Based on recent estimates on global baseline of school infrastructure, we understand that worldwide, we are expecting fatalities around 2,500 per year from earthquakes, and also for economic losses from damages. We're expecting about 3 billion per year from earthquakes and 4 billion per year from tropical cyclone. So how we reduce this risks we're facing, we probably cannot control the occurrence of natural hazards, but we all know that we can reduce the vulnerability of the school infrastructure. But looking at all this different school infrastructure around the world, we realize that we definitely cannot reach scale through a case-by-case approach, but we can group the buildings into representative typologies. And what we learned is that the key to boost efficiency of risk reduction investment is to design scalable solutions based on these identified categories of school buildings. So our experience told us that strategic planning is the essential base to realize such solutions and scale. Under our program, we've developed the Global Library of Infrastructure. We call it GLOSSy here, which is a live repository of all the school building types we identified around the world. And that's following a systematic classification system, namely the taxonomy here. And for each school building types we identified, we have quantitative fragility and vulnerability curves derived, and also corresponding cost-efficient vulnerability reduction solutions. And powered by this library, we also have the roadmap for safer and resilient schools that provide step-by-step guidance for government decision makers, from the diagnosis to analysis to planning, to actually design and implement efficient and risk-informed intervention strategy and investment plan and scale. So looking at the steps we needed to reach solutions and scale, we want to highlight that the very initial necessary step is to have a good school infrastructure baseline. And a good school infrastructure baseline will help us understand what are exposed to the hazards, where are they located, when were they constructed, why they're vulnerable, and how we can reduce their vulnerability efficiently. So now I will give the floor to my colleague Angie, and she will introduce more details about how we actually implement the GLOSSy and roadmap. Angie?
Good morning, everyone. Thank you, Jingzhe. So in some of the countries we have worked, governments do not have most of the answers to these questions that Jingzhe just presented about the school infrastructure. So in most of the cases, a data collection framework has been implemented to compile information about structural, functional conditions about the school infrastructure that could be implemented in large-scale portfolios in a systematic and sustainable way. We have 3 levels of data collection, and these levels can be directed from school communities to structural engineers to characterize and collect enough information about the school portfolio. Next slide, please. Jingzhe? Okay, thank you. To support governments addressing the needs of large portfolios instead of assessing school buildings in a case-by-case strategy, a different approach is proposed in which school buildings are characterized with a set of 12 key structural parameters that would result in a representative building that will support or identify similar vulnerabilities, deficiencies, and intervention solutions that could be implemented at a scale. Next slide, please. So the GLOSSy taxonomy classification enables technical teams to assess representative buildings and identify vulnerability reduction solutions that would not only apply to one building, but to a set of buildings. So it is critical to ensure that school buildings are strong, but also flexible enough to sustain the different loads from natural hazard events. For this reason, the GLOSSy framework aims to provide guidance to assess and identify the most cost-efficient intervention solutions to make schools safer at a scale. Next slide, please. So the challenge of scale, once understanding what are the structural and the functional interventions needed for the school infrastructure, there are 2 main questions that we need to answer. First, what is the objective of the intervention? And second, where should interventions start? So to address the first question, it is important to recognize that if we aim to the highest performance targets, the most likely situation is that interventions will not be cost efficient. For this reason, there are different scenarios with different intervention levels that we can that can be assessed to benefit as much number of students as possible. Depending on the resources available and the condition of the school portfolio, let's say a short-term performance target for interventions, for example, life safety, can be targeted, and then in a medium and long-term, allocate additional funds to reach higher target levels progressively. Next slide, Jingzhe, please. Thank you. To answer the question of where interventions should start, a prioritization scheme has been implemented and developed. In the figure presented for a school portfolio, the vertical axis represents the accumulated benefit in terms of fatalities avoided after retrofitting, and the horizontal axis, the accumulated intervention costs. To assess the level of impact of interventions at a scale, 3 cases are presented. The blue line represents a case in which the government will define the intervention order based on a prioritization parameter. This prioritization parameter is a function of the benefit in terms of life saved, the intervention costs, and the size of the school. The orange line simulates a case in which the government decides to intervene in schools in different oblasts and administrative levels. And the third one, the yellow line, presents a case of a nationwide project to intervene in schools by education level. Under this example, if the government has funds of, let's say, $100 million to invest in the school infrastructure, using this figure, it is possible to see that if a prioritization framework is used to establish the order of interventions in the school infrastructure, the benefit of life saved with an investment, with that specific investment, could be around 90% and almost 3 times compared to the benefit of if the interventions will be done or by oblast or by education level. Next slide, please. So to conclude, achieving more resilient school facilities requires a blend of scalable solutions with investments that will lead to maximum benefits, strategic planning that would support the efficient allocation of resources in school infrastructure, stakeholder engagement and policy reforms. One of the biggest challenges is the communication of risk information to community and decision makers. So it is key that they are engaged and they participate in the development and improvement of the framework, not only to support interventions of existing infrastructure, but also to ensure that new infrastructure does not have these same gaps. And of course, strengthening the capacity of the technical teams, but also local institutions is key for these projects. Thank you very much. Please let us know if you have any questions.
Thank you very much for this very interesting presentation. Important to show how what we're doing can inform the GLOSIC database, and the other way around. Based on your experience, we can probably be more compatible with what you're doing to maximize the impact of our joint work. So with your permission, I would like to move to the final presentation by Dr. Flavia De Luca on the project dissemination and international collaborations, since she will also talk about our collaboration with the World Bank.
Hi, everyone. You should be able to see my screen and hear me, correct?
Yes.
Okay, lovely. So, as Tassos introduced me before, this is the last presentation of today's webinar, and it's about the work we are doing around project dissemination and international collaboration. I am Flavia De Luca, I am Senior Lecturer in Structural and Earthquake Engineering, and in this part of the project, I am working very closely with Dr. Nicola Giordano and Professor Sextos. So, talking about, starting from the presentation we have seen before, we have a number of project deliverables that are basically focusing on the delivery of a new PSHA map, fragility and vulnerability assessment of school typologies, and community resilience metrics. All of these is embedded in the mobile and web app that Tassos has shown to you. So basically, what's next? What are the additional steps that we are taking within these projects in terms of dissemination? Within the previous part of the the webinar, you have seen that we are working closely with the global earthquake model that is part of our advisory board, benchmarking our work in terms of hazard and fragilities. And in particular, we are also closely working with our partner, the World Bank, that has been showing their global program of school. What is the target of our dissemination plan? Basically, in collaboration with the World Bank, we are planning to harmonize safer prepared school taxonomy as it is implemented in the app for Malawi within the GLOSSy architecture, so within the GLOSSy database. We have been collaborating with our colleagues from the World Bank, also from our previous project, SAFER, on resilience of school in Nepal. But there are some significant differences that we have to keep in mind between the two cases. So while the tool of the app and the framework of risk, in a sense, is the same, we are coming from the experience of Nepal was an experience in which there was a significant earthquake that occurred in 2015. So there was a significant amount of observational data collected by the World Bank and by Nepali partner. I have seen something about this, a discussion about this also in the chat today. And there was a strong community awareness because there was significant damage from the earthquake that produced, and also there was a critical mass of analytical and empirical work in terms of vulnerability from the international and scientific community. So in that case, the challenge was about harmonizing and comparing multiple sources and multiple methodologies for vulnerability assessment. So for example, in particular, we have been using some of the tools that were available from the World Bank, like the SIDA database. We have analyzed their data of damage collected after the earthquake, and also compared with the data that were in the SAFER app, so the app that was adapted for the Nepal case. And even in that case, in which damage data were abundant, I would say, because there was a recent earthquake, we had the challenge of dealing with the problem that the observational data were not enough to carry out, for example, empirical tool for vulnerabilities. And in that case, we use the tool that is basically the Bayesian updating to merge regional tools with non-regional tools. In particular, for the case of Nepal, we also made a comparison between analytical and observational fragility curves, looking at the taxonomy of GLOSSy that is presented here and was presented before, and comparing the different tools, analytical and observational. What about the case for Malawi, and what are the current activity and what we hope to achieve also with the data that will be collected through the app? In particular, in the previous presentation that was done prepared by Raffaele, John, and Nicola, there were three different main typologies for school. What the preliminary exercise that we have been doing is a benchmarking and a correspondence between the categories of school that are embedded in the Safer Prepared app with the GLOSSy taxonomy. Why we're doing this? Because this will allow to develop and target our fragilities for these typologies with respect to GLOSSy taxonomy. And in a sense, what is this going to achieve from a dissemination point of view? The GLOSSy database has also some in-country section, and the work that we are doing and the collaboration with the World Bank could provide us with a specific in-country section for Malawi, in which basically all the work that has been done in the Prepare project in terms of vulnerability and is currently done for Safer Prepared in terms of analytical fragility curves that are embedded in the app can be harmonized, and these can work as a baseline for an in-country Malawi chapter in GLOSI that would achieve our main target of harmonizing the different resources. I would like to thank you, everyone,